In this video, we're going to do a few odd problems to help you get ready to do the assignment, the even problems, for 6-1, area between two curves. And let's see, I'm having a little trouble with my pad here. There we go. The directions here for number 3. Write a definite integral in the following exercises. Write a definite integral that represents the area of the region. Do not evaluate the integral. So if we look here, we got a graph. This one is y2. It's a downward opening parabola. That's this y2 up here, negative x squared. We've got y1, the darker black parabola opening up. That is y1. And we see the dots where they intersect. So if remember to set this up, actually let's see here, I'll try this up here. We're going to go from the lower limit a to the upper limit b, and we do this as the top function minus the bottom function will give us the area in between the curves. Now the lower limit and upper limit, of course, we're going to get from the x-axis. So if I look here where we start accumulating this area, that's at x is 0. And then we go along here till we get to x is 3. So 0 to 3 are our limits. Now let me do this. I'm going to put this down here. So we're going 0 to 3. And then our top function is the downward opening parabola. That is the negative x squared plus 2x plus 3. And then we're going to minus the function that was on the bottom. That was the upward opening parabola y sub 1. And that here is x squared minus 4x plus 3. And we'll just put a dx on the end of that. Now what we could do to make, if we were going to evaluate this, to make the evaluation simpler, we could combine like terms. So what we'll do here is distribute this negative and then combine. So our integral goes 0 to 3. And we have a negative x squared. This will be another negative x squared. So there's negative 2x squareds. That's supposed to be a squared. There we go. This will turn into a plus 4x, and we already got a 2x, so that'll be a plus 6x. And then this plus 3 will get hit by a minus 3, and they'll cancel out. So we can just put our dx on there. And there we go. Number 7. I forgot to mention the last one was a red numbered problem. You could have watched that one on Calc View. Number 7 is also a red problem. If you're sick of listening to me, you can always turn on Calc View and maybe see a Gabe or Pat solve this one here. The integrand for the definite integral is the difference of two functions. Sketch the graph of each function and shade the region who's represented by the integral. So here we don't even have to find the area. We just want to graph it. So our functions here, there we go. We have our function that is on the top minus the function that's on the bottom. So I'm going to do a little kind of rewrite on here. We got 0 to 4. And our x plus 1, that is the top function. And then we are minusing, I'm just going to rewrite this x over 2 as 1/2 x. There we go. So our top function is the x plus 1. Our bottom function is the 1/2 x. Now my mimeopad is a little glitchy here in the middle, so I'm going to try to squeeze this graph down a little lower. We're going to go from 0 to 4. So 1, 2, 3, 4. And our first function, our top function, I'll do this one in blue ink, x plus 1. So we go up to 1, and then we have a slope of 1. 2, 3, oh, there's where that glitch is. Somewhere right in there. I can do it with my mouse. There we go. So x plus 1, we would go up 4 and over 4. So here is our top function. And for the bottom, I'll switch back to red. Now over here, it's negative x over 2, but I put that x over 2 or the half x into its own set of parentheses. This negative is not attached to the x. This is not a negative slope. This is 1 half x plus 0. So we would start at 0, and our slope would be 1 half, up 1 over 2, up 1 over 2. And here's where we end at 4. So if they want us to shade the region, it would be that in there until we get to 4. There we go. All right, number 17. This is a biggie. Comparing methods in 29 and 30. Well, in the book I stole them out of it, 17 and 18. Find the area of the region by integrating A with respect to the x-axis, B with respect to the y-axis, and then C, compare the results. Which is simpler? Which method will this method always be simpler? Why or why not? So let's look at our number 17 here. We got two functions, x equals 4 minus y squared, and x equals y minus 2. So let me move this up here. So right now we've got these solved for the y variable. X equals this and x equals that. So our functions are determined in terms of y. Let's do a couple things here. First, let's solve these for the other variables. So the one on top there, if I want to get the y alone, I would move the y squared over, subtract the x. So y squared is going to equal 4 minus x. And then if I square root that, this will be a y equals the root of 4 minus x. And don't forget on that the plus and minus. This part up here would be the positive radical. We are above the x-axis. And then down here would be the negative radical because we are below the x-axis. The other function here, much simpler, just add the 2 to both sides. Y equals x plus 2. So we've got the functions written in terms of each variable. And let's also, might as well find out where they intersect also, just to really nail down the points. A lot of times you cannot trust the graph. We're going to algebraically check. If we look here, it looks like this is at negative 5 comma, I don't know, maybe negative 3. This one looks about 0 comma 2. But again, graphs can be deceiving. Let's check these out. And the way we're going to do it, we'll just take these here and set them equal to each other. Since they're both equal to x, we can set these equal to each other. And I'm going to just do that. I'm going to do that down here. So I got my 4 minus y squared is equal to y minus 2. So I'm going to move everything over to the right side. The y squared jumps over there. It becomes a positive y squared. We have a plus y over there to begin with, and then we will subtract 4, so this becomes a minus 6. And now it's equal to 0. Oops. And if we factor that, we're going to get a y plus 3. And a y minus 2. So we do get our y values of negative 3 and positive 2. So here's our positive 2, here's our negative 3. That did make sense. And then we could go back and figure out the x values that go with them. So let's see here. We've got these points. Whoa. We got a y value of 2 and a y value of negative 3. So I could put those into either. I guess I'll put that into here. If I make this y into a negative 3 minus 2 is a negative 5. Negative 5 comma negative 3, that is this point. And if I put my positive 2 in here, 2 minus 2 is 0. 0 comma 2. So there's our intersection points. Now, for part A, we want to integrate with respect to the x-axis. So that means our representative rectangle will be perpendicular to the x-axis. Let's see what happens as that moves through here. So as we start accumulating area on the left, it's nice and easy to see that the top of the rectangle is touching the straight line. The bottom of the rectangle is touching the negative part of our opening sideways parabola. And that's true all the way through until we get to here. Here, the top of the triangle or the rectangle is still touching the straight line at that intersection point, but when we move a little bit beyond, Now the line is out of the picture. We have the top of the representative rectangle touching the positive radical. Let me do it like this. Up here, it'll be touching the positive radical. And then down at the bottom, that will be the negative. Oops, there's where my glitch on my pad is. This down here will be the negative of that same radical. Now, when we do part B and change everything to the y-axis, it is what touches the right side of the rectangle minus what touches the left. So even up here, we see the right side is touching the parabola, the left side is touching the straight line. And as we move from down low all the way to the top, that's always going to be true. So when we go to the y-axis, we will use a single integral. When we're going here to the x-axis, we're going to have to break it up into two integrals. So let's get started with the hard one here. Let me get rid of this. All right. So let's see. Our first integral, here we go. If we're going to the x-axis, we're going to start here at -5. And as we're going through here, remember the top of the rectangle is touching the straight line, the bottom is touching the curve. That is true until we get to x is 0. So here our upper limit will be a 0. And now it's top minus bottom. So what we're going to have there is the line, and that is x plus, oops, let me back up here a minute. Oh yeah, x plus 2. And then we are going to minus the negative radical. The negative radical of 4 minus x. There we go. And this minus and negative, that will turn into a plus. So that'll take care of this first chunk of area. And we're going to add to that another integral. Now here we are. Oops, there we go. Now we're moving through this part of the plane region. So we're starting here where the old integral left off at 0. And we're going to move along the x-axis until we hit 4. And now it's what is touching the top of the rectangle. That is our positive radical 4 minus x. And we're going to minus from that what's touching the bottom, the negative of the same radical, 4 minus x. So let me move this up here out of the way. There we go. And let's simplify this a little bit. The first part, -5, 0, or actually I'm going to do it like this. Here we got a radical minus a negative of the same, so that'll turn into a plus. And now we're just going to have 2 of these radicals. 2 radical 4 minus x. Ooh, and don't forget there's dx's on these also, both sides. Okay, so I guess we can antiderive here. This, we can just do these as individual chunks. The antiderivative of x is x squared over 2, plus the antiderivative of 2 is 2x. Now here, be careful. The inner function, that would be our u, 4 minus x, the derivative of that is a negative 1 dx. So if this was our own separate integral, we would have to tweak this with a negative, where we're going to make that a minus. We're going to raise the power by 1, so it's going to be 4 minus x to the 3/2 or divided by 3/2, or we'll bring that up and flip it and multiply by 2/3. This will be evaluated from -5 to 0. Plus, here we can pull the 2 out front, so we'll pull that 2 out. And then we're going to antiderive this just like we did over here. That is going to change this to a minus. And then we're going to have our quantity, 4 minus x, to the 3/2 power. And we're going to divide by 3/2 or multiply by 2/3. So this 2 times 2/3, we'll turn that into 4/3 here shortly. Ooh, and this is evaluated from 0 to 4. And let me get some more room to work here. And now we evaluate. Here, upper limit jumps in first, so that'll be 0 squared over 2. That's just a 0. 0 jumps into the 2x, so that's 2 times 0 is 0. And now the 0 jumps in here in the quantity, so we are going to have something here. Minus 2/3, that's a 3. Oops. And the 0 jumps in. 4 minus 0 is 0, so that becomes 4 to the 3/2 power, or the square root of 4 cubed. And just to give myself enough room here, I'm going to drag those zeros out of the way. So there's just negative 2/3 square root of 4 cubed. So that is the first integral from the negative 5 to 0. Or no, we still got to put the negative 5 in there. What am I saying? Okay, we did the upper limit, and we've got this term. Fundamental theorem says we now subtract as a quantity, the negative 5 jumps in. Negative 5 squared is 25, so that becomes a 25 halves. Negative 5 times 2, that'll turn into a minus 10. And then minus 2/3 times, the negative 5 jumps in. 4 minus a negative 5 becomes a 9. So that becomes the square root of 9 cubed. So there is the first integral done. And I'm kind of running out of room here. See if I can squeeze this down just a little bit. Or what I'll do, I'll end this parenthesis up here. And now the fundamental theorem of calculus, well, we did that one. We still got this minus in here. So now we're going to minus the evaluation of the second integral. First, well, this is going to be 4/3. 4/3, and then we jump the 4 in here. 4 minus 4 is 0. 0 to the 3/2 power is 0. So that just becomes a 0. And now we're going to minus. Now the 0 jumps in. So we're going to have a 4/3. 4 minus 0 is 4. So we're going to have the square root of 4 cubed. And now we just clean this up with a little arithmetic. So let's see here. We've got negative 2/3. The square root of 4 cubed. 4 cubed is 64. The square root of that is 8. So this will be times 8. And now we have minus, well, let's see, I'm just going to distribute this. We'll have minus 25 halves plus 10 when we distribute it to here. This will turn into a plus 2/3. The square root of 9 cubed, that would be 27. 27. Now we're right here, minus. Well, this minus, it would be a minus 0, and then that minus will distribute here and change this to a plus 4/3. And then here, again, we got 64. Square root of 64 is 8. 8. Now, I haven't checked with my notes lately. I hope I haven't screwed anything up. We'll see here. Negative 2/3 times 8, that's negative 16/3. Minus 25 halves plus 10. 20th, that becomes an 18. 18. And then I almost forgot here, this 4/3 times 8, that is plus 32/3. Okay, and just to save a little time, if you do get common denominator 6 and add those all up, you get 125 sixths square units. So the area between those curves, when we took it to the x-axis, was 125 6 squared units. Now, this is a good answer, and when we do part B, we should expect to get the same answer. Because remember, here in part B, we're going to find the same area, but just with a different technique, taking everything to the y-axis. So we know our answer, and hopefully we'll get the same answer here. So, just move this up a little bit. And like I said earlier, we should pull this off with a single integral. So now we're going to the y-axis. So let's see here. Down at the bottom, we have our lowest y value is -3. That's a 3. And we're going up to +2. And in here we'll go our function. What is touching the right side of the rectangle? That is our leftward opening parabola, 4 minus y squared, minus what is touching the left side of the representative rectangle, and in this case that's the straight line y minus 2 dy. Okay, this looks much nicer than what we just did as far as evaluating and integrating. There we go. Let's distribute the negative and collect like terms. So we are going to go from -3 to 2. Our leading term will be a negative y squared. And then we'll have a minus y. That'll turn into a +2 with the 4 we already got is a plus. Oh no, that'll turn into a +2, and with the 4 turn into a +6. So this already looks like it's going to be much nicer than the one we just had to do. So let's anti-derive. Negative y cubed over 3 minus y squared over 2 plus 6y from -3 to +2. So now be careful with your negatives here. Always chance to make a little mistake. The upper limit 2 jumps in, so we have a negative. 2 cubed is 8, 8/3, minus 2 squared is 4, 4/2, plus 6 times 2 is 12. So there's our upper limit evaluated. And now we're going to subtract our lower limit evaluated. Now careful here, mind this negative. So we have a negative, and then -3 cubed is a -27. So that'll change this to a plus 27/3. Minus, now here the -3 jumps in, the negative is squared away. This just becomes minus 9/2. And then the -3 times 6 will become a minus 18. Let's see. And I'm going to do this like this. Let's get some denominator 6's. So this term will be a negative, oops, I'm going to move this down here, -16/6 minus, well, let's do this. 4 over 2 is 2, so this is a -2, plus 12. That becomes a 10. Ooh, well, no, let's just keep doing it this way. Minus 12/6 plus 12 is 72/6. Now here we're going to distribute the negative, so this become a negative, and that'll become 54/6. This negative will hit here, that'll turn into a positive, so positive 9/2, or that'll become a 27/6. And then this will become a plus 18. 18 times 6, 60 and 4, 108, 108/6. And since it's all denominator 6, if you add and subtract all the numerator numbers, we do get the expected 125/6. Where is that? So back here, we did part A. To the x-axis, it was pretty gruesome. We did part B to the y-axis, much nicer. So part C, compare the results, which is simpler. Of course, to the y-axis, integration was much easier. In general, will this method always be simpler than the other one? Well, it depends on the functions. Here, we had the line left the shaded region, so we had to rely on the positive and negative parts on the parabola. You know, that could easily happen with respect to the other axis if the graph was rotated. So there's number 17. That's a pretty juicy one from the homework. That'll help you with, I think, 18 from the assignment. Okay, now this one, I believe in your book it's number 27. The one I cut it out of here, it's 23. And I think if I remember the directions correctly, they want you to graph it and then find the area of the region between the curves. So let's do a quick little graph here. If this was y equals x squared, it would be a parabola opening up. But since it's f of y or x equals y squared, it will be a parabola opening to the right, over here where our x values are positive. And then this, x equals y plus 2, or we could write y equals x minus 2. So x minus 2, that's easy to graph. Negative 2, y-intercept, slope of 1. Up 1 over 1, up 1 over 1. Come on. Come up, come on. So that line is going to go up this way. And the shaded region we're going to be looking for is right in here. Now the drawing is not the greatest, but if we look at it and pick out a representative rectangle, if we did want to switch this to the x-axis, in this first little bit, we would have to do the positive and negative pieces of the parabola until we get to this point of intersection here. So this one, it's going to be easier to do it to the y-axis, because if I draw my representative rectangle horizontal or perpendicular to the y-axis, the right side of that representative rectangle is touching the straight line. That would be the y plus 2. And the left side of that representative rectangle is touching the parabolic curve y squared. So this is going to be much simpler to do if we go to the y-axis. So I guess first we can set these equal to each other and find the intersection points. So if we set them equal to each other and subtract the y minus 2, we're going to get y squared minus y minus 2 is equal to 0. That will factor to a y minus 2 and a y plus 1. So we get y equals negative 1 to positive 2. So down here, this point, we're intersecting at negative 1, and we'll work our way up until we get up to positive 2. So there are our lower and upper limits, negative 1 to 2. And now our first function is what's touching the right side of that representative rectangle, y plus 2. And then we are going to subtract from that what's touching the left side of the rectangle. That would be the y squared. And that's a terrible squared. And we'll put a dy on there. And let's just put it in a descending order. It just looks a little nicer. Negative 1 to 2, we'll have a negative y squared plus y plus 2 dy. So let's antiderive. Negative y cubed over 3 plus y squared over 2 plus 2y from negative 1 to 2. 2 jumps in, negative 8/3 plus 2 squared is 4. 4 over 2 is 2 plus 2 times 2 is 4. So there's our upper limit. And we're going to subtract the negative 1 goes in there. So negative 1 cubed is negative 1 with the negative that's already out there. Turns that to a positive 8/3. Negative 1 squared is 1, so that just becomes plus a half, and then minus 2. Whoa, 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 hold the phone. When I put the negative 1 in there, that should just be a negative 1. That 8 shouldn't be there. I was thinking on the other side. So that should just be a 1/3 in there. There we go. If you get a common denominator and combine all your terms, you'll get 27/6, which reduces down to 9/2. And there's our area. Number 39, this is also a red problem. Let's see. So yeah, so you could watch Gabe or Pat or somebody solve it. I believe in the WebAssign, this type of problem might be multiple choice. So we want to find the area between these curves, and I believe in this one too, they did also ask for a little sketch. So cos x from 0 to 2 pi. Remember, cos starts at a peak at 1. It ends at a peak at 1. And it's going to have a valley down here at -1. So it's going to look a little something like this. Now the other one, 2 minus cos x, it's a negative cos x, and we're going to have to bump it up here to the baseline at 2. And since this is our baseline for our second function, and it's negative cos. Negative cos will start in a valley, and then it will end in a valley, and it'll have a peak in the middle. This peak would go up to a height of 3 on the y-axis. So we're finding this region here. So now that we got it graphed, we can see our top function is the 2 minus cos x, and the bottom function is the cos x. And if I draw a representative rectangle horizontally, if we wanted to take this to the y-axis, it's going to turn into quite a chore. If we stick with the x-axis integration, the top of the rectangle is always touching the red curve, the bottom is always touching the black curve. Okay, I think I'm going to start a new slide to set this integral up. So let's see here. We are going to go from 0 to 2 pi. The function on top, we already said, is the 2 minus cos x. And then we are going to minus the bottom function, which is just cos x dx. So we can combine some terms here. 2 minus, we have 2 negative coses of x, so that'll just become minus 2 cos x. Oop, there we go. Nope. There we go. Dx. And let's antiderive with respect to x. The antiderivative of 2 is 2x. And then we're going to have minus 2 sine x. And we will evaluate that from 0 to 2 pi. So let's see, the 2 pi jumps in here. 2 times 2 pi is 4 pi. Whoa, I ran into the glitch there. So let's see, 4 pi minus the 2 pi is going to jump in here. 2 sine of 2 pi. And now we'll minus the lower limit evaluated. The 0 jumps in here, so that'll be a minus of 0. And then minus 2 sine of 0. 2 sine of 0. Well, let's see. The sine at 2 pi is 0. The sine at 0 is 0, so those are gone, and that's just a 0. So it looks like our answer is 4 pi, or approximately 12.566. 12.566. I would just leave it as 4 pi. All right, and that is our last odd problem. I hope this video helped.